Hi friends, welcome back to Edupedia world. Last class we discussed the concept of electromotive force, terminal voltage and the internal resistance of a cell. Today we'll shift our focus to resistance in combination. We'll see resistance in series, in parallel and combination in which both series and parallel coexist. We'll understand what is the basic difference between them, how to simplify the circuit for each case, and also the basic properties for each situation. So let's start with resistances in series. Today's lecture will be focused on combination of resistance. Combination of resistance. Now what do I mean by combination of resistance? What it means is that we can attach multiple resistance to a circuit, and the way the resistance are attached, they can either increase the overall resistance or they can decrease the overall resistance. So if we have 5 resistance and 10 resistance, resistance of 5 ohm and 10 ohm, and if we want to increase the resistance, then we will attach it in what is known as a parallel rather series manner, and if we want to decrease the overall resistance, then we will attach it in what is known as the parallel manner. So to roughly say about the combinations of resistance, we can have either resistance in series, we can have resistance in parallel, or we can have a combination. But this is trivial because once you know series and parallel, then you can make it out how to approach a combination condition. Fine. Let's start with the series scenario. Now suppose we have a circuit like this. We have a battery. For the case at hand, while understanding series and parallel and combination of resistance, we'll ignore the internal resistance of the battery just for understanding sake. Okay, now what we'll do is we attach a resistance R1 and we attach another resistance R2. This is my complete circuit. This is positive terminal, negative terminal. Okay, and let's say this is a terminal voltage V. So even if there is internal resistance, we are taking the terminal voltage, so it does not matter. We are not taking EMF. If we took EMF, we needed to take the internal resistance into account, but I am ignoring it and taking the terminal voltage instead, right? Then this is R1, let's say, and this is R2. Now what I mean when I say equivalent resistance is that what is a single value of a single resistance that I can replace this combination with, and the amount of current drawn will remain unaffected. So instead of R1 and R2, I need to replace a resistance R such that this whole scene remains same, that is the current drawn remains the same. Okay, in this case let's say a current drawn is I. Now what I'm saying is that I want a scenario like this. I want a single resistance to replace the two resistance, and that single resistance will be of a resistance value R, but that will result in same current being flowing I. Okay, this is what we need. This is what we need. In order to approach the problem, you need to understand the matter that, let's say A, B, C, these points are A, B, C, and then let's say this point's potential is VA, this is VB, and this is VC. Therefore, what we can say is this potential drop VA to VB and this potential drop VB to VC should be equal to the whole potential drop here, right? Because parallel to this concept, this point is A and this point is B. Fine. And let's say this VA, VB, VC and this R1, R2, through every point and every resistance the same current I will flow. Why so? Because there is no alternative path for the current I. It has to, the current going through I here should be the same current flowing here, should be the same current flowing here throughout. Okay, so what we can do is we can find the potential difference VB minus VA, and how much will that be? That will be equal to current times R1 by Ohm's law, I times R1. Okay, and if we find out VC minus VB, that is this potential minus this potential, it will be again the same current I, because it is the same current flowing throughout, multiplied by R2, isn't it? Now, therefore what we can say is the current difference or the potential difference between VC and VA, what can that be written as? VC minus VA is this equation minus this equation, or sorry, this equation plus this equation. If we add this plus this, then this and this cancels. VC minus VA, that's what we get, and that turns out to be IR1 plus IR2, which is equal to I times R1 plus R2. Therefore this VC minus VA is I times R1 plus R2. And what is VC minus VA? VC minus VA can be basically written as this point minus this point. There is no resistance, so this point is VC and this point is VA, and that this potential difference is nothing but the potential difference V, that is the battery terminal voltage. Okay, so this is our initial scenario. Now I want to replace it with this circuit, and let's say this is point D and A, just not to confuse with these points. So VE minus VD can be written as I times R, similar to what we have done here, but just replacing the resistance with R, that is the equivalent resistance. And we know that VE minus VD is like this difference, that is the terminal voltage. Therefore this turns out to be V is equal to I times R. Now if we equate this and this, then what we'll get is I times R1 plus R2 is equal to I times R. This implies the resistance R, that is R equivalent, which is replaced, is R1 plus R2. Fine. So we can say that if two resistances are in parallel, rather in series, this is series, like, right? In series what happens? They are, this end of one resistance is connected to the other end of the other resistance, and if there were one more resistor there, that would have been here. So just to, for completion's sake, if there were three resistance in series, that would be like this. Okay, so what we see, if resistance are in series, then the resistance add up, the equivalent resistance. Similarly, if we had three resistance like this, and this was R1, this was R2, and this was R3, and this was replaced here, then R equivalent, or R, can be written as R1 plus R2 plus R3. So all the resistance that we keep on adding in series will be just numerically added, algebraically added, R1 plus R2 plus R3 plus R4 till Rn. Okay, So what happens in series? We see two things. One is that the current through all the resistor is the same. Second is that the resistance adds up. As a result, the effective resistance, the end resistance, will be more than individual resistance. R will obviously be more than R1, and it will be also more than R2, because resistance cannot be negative, they has to add up. Fine. So in series, the resistance add up, the effective resistance at the end is larger than the individual resistance. Now let us see the case of resistance in parallel. As you might have guessed already, in parallel the resistance has to be parallel to each other. Let me draw the circuit here. We will have a battery, and then parallel resistance would be something like this. I will explain you. Terminal voltage V, this is R1, this is R2. Now what is happening in parallel resistance, parallel scenario, is that the resistance meet at both the ends. The resistance which are in parallel will meet at both the ends. They have a common end here and they have a common end here. If there were a third resistance which was parallel, that would again come out of here, and there would R3 like this. Fine. I hope you get the idea what is the parallel resistance, in contrast to the series, which was like a straight line. Here they are just two parallel paths. Okay, now since they are parallel, one thing that you can note immediately is that the potential difference between R1 and the potential difference between R2 is the same, because this point and this point are same, isn't it? If this is A point and this is B point, then basically this is VA, potential at A, and this is VB. Therefore both across R1 and R2 there is same potential difference, potential drop, and that is characteristic of a series parallel resistance. What is different from the series? The difference is that now the current will not be the same. Why so? Because if we think about it, let's say a current I is flowing here. Once it reaches here, it will have two paths. Current can either go in this direction or it can go in this direction. So the current breaks up. Let's say a current I1 flows in this path and a current I2 flows in the other path. Therefore, because current has to be maintained, current cannot be destroyed. Therefore, the total current I will be equal to I1, that is through resistance 1, plus I2, that is through resistance 2. Okay. Now using this idea, let us find the equivalent resistance. The equivalent resistance circuit will be same as here. Basically we want to replace these two resistance with this resistance R. So I am not going to draw this again. Now how do we find the equivalent resistance? In order to find the equivalent resistance, we will take help of this condition, that I should be equal to I1 plus I2. Now what is I1? I1 can be written as, using Ohm's law, we know that I1 will be VB minus VA, that is the total potential drop, upon the resistance R1, isn't it? This is my potential drop and this is my R1, therefore I1 should be potential drop upon resistance. Similarly, I2 can be written as, again, VB minus VA upon R2, isn't it? And if you think about VB minus VA, this will be VB minus VA will be nothing but the potential drop V, the terminal voltage. So I can replace it with V upon R1, and this I can replace with V upon R2. Okay, now I have this equation and these two equations. I will replace these values in the first equation, equation 1, and that will give me I. Now what will be I? From here I can see that I is V divided by capital R. Let me use a different color. So using this equation, what I can get is I is V divided by capital R, and I1 is V divided by R1 plus V upon R2. And if we simplify this, V's will cancel out, and what I get is 1 by capital R, that is 1 by equivalent resistance, is 1 by R1 plus 1 by R2. Therefore, if resistance are parallel to each other, their reciprocal add up to give the equivalent resistance. Okay, this is the resistance adding up in parallel condition. This is my parallel and this was my series. Now suppose instead of two resistance, if there were n resistance parallel to each other, then what would we have done? Then 1 by R equivalent would have been 1 by R1 plus 1 by R2 plus 1 by R3, adding up till 1 by Rn. Okay, fine. Now for the case of two resistance in parallel, if we simplify this, then we can get something like this. 1 by R is taking LCM R1 R2 R1 plus R2, which means R is R1 R2 by R1 plus R2. So this is a shortcut formula if there are two resistance in parallel. You might remember if you want to, but this you need to remember, then you can easily calculate the numericals. Fine. Now the characteristic properties of series combination of resistance. One is that, as we have seen, the potential difference drop across them is the same. Second is the current branches out, and the current branches out, but they add up to be the equivalent current. Third, if you see this, if you observe it mathematically, then what you will find is that the equivalent resistance that we get, right, the equivalent resistance that we get here will be less than each individual resistance. It will be less than R1 and it will be less than R2. So contrast to the series resistance, parallel resistance results in a reduction in the equivalent resistance. Let's see both parallel and series and compare them once. In series, the current was uniform throughout. In parallel, the current breaks out. In series, there was individual potential drops, but in parallel there is same potential drop. In series, the resistance add up and becomes larger. In parallel, on adding up resistance, they actually become smaller. Okay, so this should give you an idea about both series and parallel resistance. Now, what is a combination resistance? Basically, a combination resistance would be one where we have both series and parallel. How to approach those scenarios? Let me draw a simple diagram. Let's say we have something like this. You have a battery and you have one resistance here, and then here it branches out and becomes two resistance. Okay, so now the question will ask you to solve this. If this is R1, this is R2, this is R3, and this is our V, how do you approach this case? Here what you have to do is see it as two independent parts. Think about it as two independent parts. One is, here is a combination of resistance in parallel. First you solve this. Okay, as a result of solving that, you will get a single resistance. Now that resistance you replace for these two resistance, and now that single resistance will be in series with this R1. You can solve two resistance in series. As a result, you will get a single resistance combining all the three of them, and then it becomes a trivial Ohm's law application. Fine. So you have also seen an example of how to approach combination of resistance now. This class have given you an idea about different combination of resistance, and the previous class introduced you the concept of the potential and internal resistance, terminal voltage, those things. Using the knowledge gained in today's class and the previous class, we will focus on numericals in the next class, and that will help us build on the knowledge we have gained here. So till next class, have a great day. Goodbye.